Welcome to the video podcast series dealing with electrochemistry. We're going to specifically start a three-part series with electrolytic cells. And before you watch this series, I highly recommend that you watch the series on voltaic cells and the Nernst equation calculations so that you can set the comparisons that we're going to make into a proper context. Welcome. A brief comparison of voltaic cells and electrolytic cells. In voltaic cells, electrons are generated at the anode, so the anode is negative, and electrons are consumed at the cathode, so it is positive. For electrolytic cells, electrons from an external power source are supplied to the cathode, so it is negative, and it removes them from the anode, so it is positive. It's important to know that the electrons themselves come from the anode. The external power source essentially just moves them from the anode to the cathode. Further comparisons as we look at voltaic cells, delta G, which is Gibbs free energy, is less than zero. Voltaic cells are spontaneous, and the energy of the cell is greater than zero. The electrode, the anode is where oxidation takes place, and the sign or the charge there would be negative. The cathode is where reduction takes place, and the sign of the charge there would be positive. We looked at the voltaic cell last. Let's look at an electrolytic cell. In an electrolytic cell, delta G is greater than zero. An external power source is required to make this reaction happen, unlike a voltaic cell where the reaction would be spontaneous, and the energy of the cell would be less than zero. The anode oxidation takes place, but the charge on the anode, the sign would be positive. At the cathode, reduction takes place, but here, opposite that of a voltaic cell, the charge is negative. So that's a comparison of voltaic and electrolytic cells, and keep that in mind as we continue. The word electrolysis is an interesting word. Those of you who have had biology or anatomy know that the process of lysis refers to splitting or cutting something off. Here, the process of electrolysis is effective in decomposing certain compounds into its elements. We often use this in industry for the protection of elements such as chlorine from molten sodium chloride, copper, and aluminum. When we look at the process of electrolysis, we can easily predict the products from a molten salt. And when we think about salts, think of ionic compounds. If the molten salt is pure, the cation, which would be the metal, is reduced at the cathode, and the anion, the nonmetal, is oxidized at the anode. For instance, let's look at potassium chloride. K plus is reduced to potassium metal at the cathode, and then the chloride ion, 2Cl minus, is oxidized to Cl2 at the anode. I like this slide so much, I'm going to show it to you twice. So here we go. We said before that when you have a pure molten salt, it's easy to predict the products from an electrolytic process. It's much less easy to predict them from a salt that's dissolved in aqueous solution because of the presence of the water. Water can be more easily reduced than many metals, so voltage applied will bias toward the reduction of water than the metal cation. We're going to begin a series of slides with undeniable truths, and these are some general principles that guide our thinking about electrolytic cells. It will be helpful to you if you pause the podcast at each slide and take notes, put into your own words what is displayed for you here. If you do that, it'll help that to get into your head a little more easily. Now, here are undeniable truths. The more easily oxidized species, meaning the stronger reducing agent, reacts at the anode. If you're given two or more of these species to compare and to predict which will react at the anode, the one with the more negative reduction potential or the more positive oxidation potential, depending on what they give you, would be the one that will react at the anode. the more easily reduced species, the stronger oxidizing agent, will react at the cathode. Remember, an oxidizing agent is one that has an attraction for electrons in an oxidation-reduction reaction, so it's more easily reduced. In terms of us comparing more than one of these that you're given, the more positive reduction potential would be the one that would react at the cathode, or the less negative reduction potential, depending on whether you like your glass half full or half empty. So the standard table of reduction potentials refers to a change from aqueous ions to the free element. The standard reduction potential cannot be used to tell the relative strength of oxidizing and reducing agents, and that is because it always refers to the change of aqueous ions to a free element. I want to emphasize this. When you're given a problem dealing with electrolytic cells, they're generally going to give you what the reduction or oxidation potentials are for you to compare. This would not be the time to use the standard reduction potential table that's provided on the AP test or that's in the back of your textbook. Partly because electrolytic reactions are not happening under standard conditions, and because they always refer again to aqueous ions to free element. They're just not useful in this. What will be useful in predicting which ions will gain or lose electrons more easily, we have to look at our periodic trends. Metals to the left and down on the periodic table will be oxidized more easily. Nonmetals to the right and up on the periodic table will be reduced more easily. Predicting which elements can be prepared electrolytically, aqueous cations are reduced at the cathode from solutions of their salts is based on the following criterion. Cations of less active metals are reduced to the metal, and the less active metals some examples are gold, silver, copper, chromium, platinum, and cadmium. We are looking at cations in aqueous solution as we look at this particular undeniable truth. When salts include active metals dissolved in water, and those active metals would include groups 1A, the alkali metals, lithium, sodium, potassium, rubidium, cesium, francium, and 2A, the alkaline earth metals, beryllium, magnesium, calcium, strontium, barium, and radium, and aluminum from group 3A. These are not reduced in aqueous solution. Water is reduced to H2 and OH- instead. Anions that are oxidized because of overvoltage from O2 formation include the halides, although the voltage for the chloride ion must be high, except for fluoride ion. Fluoride ion will not be oxidized. Anions that are not oxidized include fluoride and the common oxoanions such as the sulfate ion, the carbonate ion, the nitrate ion, and the phosphate ion, because the central nonmetal, which is sulfur, carbon, nitrogen, or phosphorus respectively, it's already in its highest oxidation state. So when you have fluoride ion or the sulfate, carbonate, nitrate, or phosphate ions, you're not going to see those oxidized. Instead, water will be oxidized to O2 and to H+. I want to give you as an aside a very brief simplistic definition of overvoltage. It's the extra voltage that must be applied to a reaction to get it to occur at the rate at which it would occur in an ideal system. And there's a wonderful discussion of this on Wikipedia that I would refer you to. In my experience with the AP test, I've not seen a question dealing with overvoltage, so if you are interested, you can pursue that, but that's all I want to say about it. Well, we have come to the end of this first part of the electrolytic cell. I want to leave you with a quote from Benjamin Disraeli: "Courage is fire and bullying is smoke." Stay tuned for the other parts, and I wish you well.